So far, all we've dealt with in PLCs has been discrete, or sometimes called digital, signals, which are just really an on-off signal of 24 volts. Some PLCs have 120 volts, they can have DC, they can have AC, but ours is 24 volts DC. There is no intermediate states, it's either on or off, and it stores a bit of 1 or 0. When our PLC, when there's a 24 volt applied to an input channel, but 24 volts positive, it will write a 1 to that address, and when it's 0 volts, it writes a 0. So now we're going to look at analog signals as we've used in instrumentation. Signals with like an upper and lower range or lower value. Intermediate values can occur, so it's not just a 1 or a 0. So we have a 4 to 20 milliamp, 1 to 5 volt DC, 0 to 5 volt DC, 0 to 20 milliamp, and minus 10 to plus 10 volts DC. So it's a matter of conversions. The analog module converts voltages and currents into numbers, and the numbers are manipulated by the processor. In turn, the processor writes numbers to the analog module, and the analog module converts the numbers into voltages and currents. Here's a picture of the MAD42, the analog module, which is actually in our PLCs. This module converts from analog to digital, module analog to digital, MAD, and it has 4 input channels and 2 output channels. So that's where they come up with the 42, so it's actually a MAD42. Let's talk a bit about resolution. Resolution is the total number that the processor reads as a signal or converts or sends a signal out to be converted. In this case, with the MAD42, it has a resolution of 12,000, 0 to 12,000. That's basically the span of our unit. So each analog signal actually has a span. The span is represented by a number. MAD42 has this 1 to 12,000 revolution. Each span is divided into 12,000 little individual parts. As an example, a 4 to 20 milliamp signal is represented by the numbers from 0 to 12,000, where 0 would be 4 milliamps and 12,000 would be 20 milliamps. Okay, so let's do the math. 4 to 20 milliamp signal, if 0 represents 4 milliamps and 12,000 represents 20 milliamps, let's look at 50% signal. Well, 50% signal of a 4 to 20 milliamp signal is 0.5 times 16, which is the span, plus 4, which is the offset, comes out to 12 milliamp. So 50% of 12,000, because it goes from 0 to 12,000, the span is 12,000. So, and there's no offset, 0.5 times 12,000 comes out to 6,000. Therefore, 12 milliamps is represented by the number 6,000 in the MAD42. If the unit is properly configured, an analog input will receive a 12 milliamp signal. It will actually convert that to a 6,000, the number 6,000, for the processor. An analog input is sent 6,000, it will actually send out to the real world, out to the devices in the real world, 12 milliamp. The exception to all these is actually the signal that goes from minus 10 to a plus 10 volts DC, and that actually operates between minus 6,000 and plus 6,000. But we're not going to discuss that in our course here. Okay, let's really look at this, because this is really the real world. So each analog channel actually has an overrange. Due to the fact that there could be miscalibration of transmitters or real world field devices, there is an overrange of plus or minus 600. As you know, there a common current signal, which would go from 0 to 12,000, can take overranges of minus 600 to 12,600. Once it exceeds these numbers, especially the lower range, it will actually go to an unusually high number, signaling to the processor that this is an invalid signal. Okay, so how do we tell the analog module what to go do with itself, or how it's supposed to react to things in the real world? Well, what we have to do is we have to configure it. And these modules are configured by writing a hexadecimal number to the module itself. We create the hexadecimal number by a procedure which is set forth by the manufacturer. Okay, and the number is written, yes, written to the output channel from inside the PLC. They do this by use of a move instruction, and it's done right at the first cycle using the first cycle flag. So as soon as the power is turned on to the PLC, these numbers are written directly to the MAD42 module. Let's take a look at channel numbers for the MAD42. The MAD42 will take over the next available channels that are on the CP1L. And the manual says, let's say that N is the last output channel used. N plus 1 is actually the next available channel. And in our case, where our last channel that we used was 101, the next available output channel will be 102. As the manual says for the input channels, M is the last input channel used, so M plus 1 would be the next available analog input channel. Since our last channel we used is 1, the next available channel will be 2. Okay, so that makes analog input 1 is actually channel 2, analog input 2 is channel 3, analog input 3 is channel 4, and analog input 4 is channel 5. When it comes to the analog outputs, analog output 1 is channel 102, and analog output channel 2 is 103. The hex number actually is what they call a set data word. It's written right to a word or a channel. And this has to be configured. The input channels are coded by 1 nibble, as are the output channels coded by 1 nibble, and the nibble is 4 bits. So you see here in the table next to it says enable is for on and off, which you see enable. If enable is just turning it on and off. So if I put a 1 in that bit, it'll turn it on. If I put a 0, it turns it off. The averaging is for signal dampening, because sometimes you have a lot of noise with signals, and that can cause havoc when trying to control a process, because the number is bouncing all over the place. As we've done seen in instrumentation, our meter actually will jump by a few decimal points, and the PLC is sensitive to this. The last two are shown are range codes, and they are a series of zeros and ones set forth by a table that we'll see later that tells the input or the output what type of signal it is reading. Okay, so this is the set data word for the output. The output channel are coded somewhat similar to the input channels. They use just 1 nibble, okay, but they have an enable. They don't have an averaging. Their range code is actually 3 bits. The enabling, again, is turning it on and off, and the range code is the type of signal span, like if it's voltage or current, and what type of voltage or current signal you will see. Here are the range codes for the input channels. As you see there, common ones that we would use is like 1 to 5 volt or 4 to 20 milliamp. 1 to 5 volt is 10. 0 to 5 volt is 11. 0 to 10 volt is 01. And this is entered into the range code for each channel. You probably noticed by the range code chart that both the 1 to 5 volt and the 4 to 20 milliamp signal actually have the same range code. The reason that is on the input to this analog module from the real world is a 250 ohm resistor. So if I have 4 to 20 milliamps flowing through that 200 ohm resistor, if you do Ohm's law, what you'll find is that actually generates a 1 to 5 volt signal. So the analog card really only reads the analog module really only reads 1 to 5 volt, but that resistor that's built in there converts that 4 to 20 milliamp signal into the 1 to 5 volt read by the module. The output range codes are actually 3 digits. There's a selection here of types of analog signals you can use. 4 to 20 milliamp is 100, 1 to 5 volt is 010, and they will be entered shown in the following slides. Here's how we would configure the analog's inputs and outputs. What we have here, seeing across the top, is analog output 1, analog input 2, and analog input 1. What we have here is the desired signal that we require for each one. Now, as in fact of this one, what I'm going to do is I'm going to select that I want to enable it, means I want to turn it on. And it's an output, so I look for the range code for 4 to 20, and I see here the range code is 100. So I type in 100. Now, for the next one, I have here analog input 2, and it's 0 to 5 volts. Okay, so I want to enable it, so I'll select 1. I like the averaging to maintain a smooth input, and the range codes, the two R's here, the range code is actually 1, so I type in here 1, and another one here 1. Okay, for the last one, analog input 4 to 20 milliamp, I look here, the range code for 4 to 20 milliamp is 10, so I select enabling, I select averaging, and then what I select here is 10. Okay, so it says here what we're going to do is write the word to n plus 1. Well, that write address is the output address, or the output channel that we last used for discrete and plus 1. So our last output channel is 101, so this one here is going to be 102. Okay, so now what I do is I'm going to go to the next set here, and I look at 0 to 10, analog output 2, 0 to 10. So I look at the range code here, 0 to 10, which is 001. And first of all, I'm going to select 1 for enable, and then 0, 0, 1. So that gives me 0 to 10 volts for my analog output 2. Now analog input 4, what I desire here is 0 to 10. So I look at 0 to 10 for analog input. The range code is 01. So first of all, I say yes, I'm going to enable it. That means turn it on. I want it to average because I want to maintain that smooth rate. And I enter in the range code for 0 to 10, which is 0, 1. The last one, analog output 3, I have here minus 10 to plus 10, and it's an input, so I go to the range code here, which is 00, and I'm going to select enable, and I'm not going to select averaging, just for the example of just not doing it. So I would put in a 0 there, and then what I put in is the range code for that particular type of signal, which is 0, 0, and the address to write that to is n plus 2, which now becomes 103. That's where I'm going to write this set data word to. Okay, now let's look at converting our data from the simple binary bits we have, ones and zeros, into hex numbers. As an example, look at analog output 1. What we have is 1100. I find it a lot better to do it nibble by nibble instead of doing the whole word all at once. Less mistakes can occur that way. So I enter this as a binary number in my calculator as a programmer. Okay, so I type in 1100, and what I end up with is a C for the hex number. And as you can see, in what I have entered is a C in my my configuration table that I'm going to use to make up my set data word. The next one, right next to it, is analog input 2, and it is 1111. So if I clear this, I enter in 1111, and what it gives me here is an F, and I enter the F into my F here into my table for analog input 2, and let's look at the last one there next to it. is 1110. So I clear this and I type in 1110. Okay, and it gives me an E, and that's what I have entered into it. So I end up with a hex number, which is 8CFE, and that's what I'm going to write to my analog output 102, and that is going to configure my MAD42 module. Here are the lines that I will program into my CP1L that will configure the MAD42 module. If you'll notice that there's two lines with move statements. The top line move statement takes our first source word that we made out of our table, 8CFE, and notice that there's the hashtag in front of that that tells it that it's actually a hex number, and it moves it to 102, which is the first analog output channel. The line below, it moves the other hex number that was created in the sheet. We didn't show it in the movie, but it was still created. If you notice the sheet in the previous slides. So we take 89D8, which is actually a hex number, putting a hashtag in front of it, and we write it to 103. Both lines are controlled with a first cycle flag, which means that even though you load up the program, those numbers will not be sent to that module until the power of the PLC is cycled. Then it will read or send out correct signals. Okay, what I have here in my my program, I actually have taken those hex numbers and I'm using a move instruction to write 8CFE to 102, which is analog input number 1, and 89D8 into analog output number 2, which is 103. What I do to move these, I use a first cycle flag. That means that they will be moved when the cycle or the power to the PLC is cycled. Right now I've actually uploaded this program, but I haven't cycled the power. And if you'll notice that if I try to change the analog output number 2, which is 0 to 10, and you can see on the meter, I'm going to give that a 50% signal, which is 6,000. I hit enter. What you should see on the meter there is actually 5 volts, which should be 50% of 0 to 10. Also, too, you see on the analog input, I'm varying it on analog input number 1. You should actually see a change of numbers. If I set this to 12 milliamp, what you should see in analog input number 1 here, what you should see is 6,000. So what I'm going to do, I'm going to cycle the power to this PLC. Turn it back on. Now what I'm going to do is reestablish communication. And once I do that, what you'll see is you now see that in analog input number 1, it's actually showing 6,021. Now I'm going to vary that analog input. And as you can see, as I increase this, and I'll take it all the way up to 20, there we are, 20, which is full scale, what you see here is it actually is 12,006, 7. It's bouncing a little bit, but at 12,000 is full scale. Now, if I take that down to 4 milliamp, get this down to 4 at 4 milliamp, and what you see here at 4 milliamp, I'm a little bit low according to my calibrator. But what you see here, let's get that. It's very difficult to get it right on. As you can see, I'm very close to 0. A PLC is actually very accurate when it comes to measuring analog signals or sending out analog signals because it has a resolution of 12,000. That means it can adjust the output or read the input to an accuracy of 1/12,000th of the total signal. Okay, so you can see now, as to answer the question of what happens if I go too far below, I'm lowering the signal down. I get it down to about 3.5. I still read a negative value in an analog input number 1. Okay, as I lower this down, as soon as I get below 3.2, as you can see, what happened is the number went to a negative 32,768, which is a totally ridiculous figure. And you can figure the PLC that when it gets this number, it just shuts everything down. That's how they can do the fail-safe with the 4 to 20 milliamp signal. So adjust that up. Now, just to demonstrate the analog output, what I'm going to do, I'm going to type in 60 or 50% signal, which is 6,000, to analog input or analog output number 2, and what you see is what I get there is 4.99, close enough, 5 volt. And if I was going to take which one's going to be correct, I honestly would say the PLC. Let me try this at full scale, which is 12,000. I enter that, and what I get is 9.97 volt. For the 12,000 I have here, sent that. So what you can see is the PLC takes that number and it sends it to the analog module that converts that number into a analog signal. Consequently, with the input, it takes the input signal, the module takes the input signal and converts it to a number and sends it to the processor. Okay, so what I'm going to do, I'm going to take this, I've got a battery here, which is a 1.5 volt battery. I'm actually going to connect it up to analog input number 2. When I touch to the battery, what you can see is I'm reading 3843, which is actually a little over 1.5 volts. So I would say that this battery is pretty good. Mind you, this is a very expensive battery tester. Take the battery off, and as you can see, it dropped down to near 0. Okay, so what we've seen, we write to the analog module. It has to be cycled through power using cycled when the power is initialized when the power is cycled. And what you see here, it's done through the first cycle flags. Once it's been cycled, now it will read or send out the what we want by the analog module. Okay, let's look at doing some math here with word values and signal. Let's calculate a signal from a word value. The equation is the signal is equal to the word value divided by 12,000 times the span plus the offset. Very similar to what we did in instrumentation. So if you have a 4 to 20 milliamp signal and the word value is 7,500, the signal is 7,500 divided by 12,000 times 16 plus 4, and that comes out to 14 milliamp signal. Okay, let's look at calculating a word value if we have a signal going to a PLC. Word value is equal to the signal minus offset divided by span times 12,000. So we need to know what type of instrument signal it is. It's 1 to 5 volt signal with a signal value of 2.75. So to get the word value, you take 2.75 divided by the offset of 1, divided by the span of 4, and multiply by 12,000, which gives us 5250. All right, let's look at calculating that battery's voltage from the word value that we've got from the PLC. So the signal is equal to the word value divided by 12,000 times the span plus the offset. So we take 3843, divide it by 12,000, and multiply it by 5, which is the span, and the offset is 0, so we add 0. What we end up with is 1.6 volts. So the battery actually is a little over 1.5.